rotate using Fleming's either the left hand rule or the right hand rule. If it is a DC generator, then it will rotate based on Fleming's right hand rule. If it is DC motor, then it will operate based on Fleming's left hand rule. And DC generator is used to convert mechanical energy to electrical energy. That means electrical output can be obtained from DC generator, whereas DC motor can produce mechanical output from the electrical input. Right? So electrical energy can be converted to mechanical energy by using DC motors. So here in this experiment number 8, we will see how speed can be controlled in case of a separately excited DC motor. DC motor can be of many types, right? It can be separately excited DC motor. There is one more category named as self-excited DC motor. Under self-excited DC motor, there are three categories once again: series motor, shunt motor, and compound wound motor. All the constructional details, their characteristics, their performance, behaviors, everything will be discussed in the theory class. In laboratory class, we'll only learn how to perform this experiment, how to control the speed of a DC machine, how to draw the torque speed characteristic curve of separately excited DC machine after the experiments, from the experimental results. Okay. So there are many components, there are many parts. They are stator, they are called field, there are brush arrangements, commutator arrangements, different compensating windings, etc. Yokes, frames, all are the components or parts of a DC machine, right? So what is the basic working principle? As I told just now, that it is just like a current carrying conductor placed inside a magnetic field. You have seen in module 2 in basic electrical theory class, in module 2, well, I have discussed about the single phase sinusoidal voltage generation, how sinusoidal voltage can be generated if a coil or three numbers of coils are placed inside a magnetic field, right? That means whenever a current carrying conductor is placed inside a magnetic field, it will experience a force. It will experience a force, and this force will be dependent upon three major factors. One is called the flux density, one is called the current, and the third one is the length of the conductor which is placed inside the magnetic field. Okay, so it is like there are two magnetic poles, say North Pole and South Pole. Magnetic flux lines are flowing from North Pole to South Pole, and you have placed a conductor under this magnetic field. AB is the conductor or a coil which is placed, which is carrying current, right? So it will definitely experience a force, capital F, which is equals to B times I times L, where B is the flux density in Weber per meter square, I is the current flowing through the conductor in ampere, and L is the effective length of the conductor in meter. Right? and the direction of the force on this conductor will be determined by Fleming's left-hand rule. Right? So what is that rule? If you extend your left hand in such a way that thumb, forefinger and middle finger are making an angle of 90 degrees by each other, and if the forefinger is indicating the magnetic field and the middle finger is indicating the direction of current, then definitely your thumb will indicate the direction of the motion of the conductor. This is Fleming's left-hand rule, and following this rule, the motor, DC motor, will operate. Right? So, DC motor has two parts. One is called armature, one is called rotor. Definitely, armature is the stationary part of the motor, and rotor is the rotating part of the motor. Right? Rotor will rotate only. Stator will be fixed. Okay. So, as per the working principle, what I have just explained, that if a current carrying coil is placed under a magnetic field, it will start its rotation. Right? Now, what is the input here? It is the electric current, that is electrical energy. And what is the output we are getting from the machine? The rotation of the rotor. Right? So here actually the electrical energy is getting converted into the mechanical energy. That is the working of DC motor. And when the motor will start its rotation, definitely it will rotate with the speed. And this speed needs to be checked, monitored always. This speed is required to control by controlling some other parameters like the armature voltage, or it may be a field current. Okay, your rotor is just like a field. Rotor is just like a field. So either the armature voltage or the field current, these two are responsible parameters for the control of speed of the DC motor. Right? And why this speed control is required? Why we need to study speed torque characteristic curve? Right? Because depending upon the speed torque characteristic curve, we'll be able to understand that how speed is varying with the variation of torque, because the speed, torque, these parameters are related with the motor output voltage, the armature current, as well as the field current. So many parameters are dependent on the speed and torque. Okay, and by changing the speed, by controlling the speed, actually you are controlling the voltage, the armature voltage of the motor. Okay. Now, let us move on to the experimental part of today's experiment. This is the theoretical response of speed torque characteristic curve of a separately excited DC motor. Now, what is the difference between this separately excited motor and self-excited motor? A separately excited motor means field winding will be excited separately. Field winding will be excited separately. You can see these two circuits drawn in this page. They're basically the equivalent circuit of the DC motor, right? Where the first one is showing the armature and the second one is showing the field winding. You can see field winding. This is the field winding. Follow my cursor. This is the field winding. And this is the motor. This is the motor. And these two terminals marked as 1 and 2 are called the armature terminals. And this RA is nothing but the armature resistance. Okay, this IA is the armature current. VA is the supply voltage. That is the DC supply voltage. This VF is also a DC supply voltage. This VF is required to supply the field coil, to supply the field winding of the DC motor, because it's a separately excited DC motor. So the field winding should be excited separately. Okay. Whereas in case of self-excited DC motor, the field winding will be excited by the DC supply connected with the armature itself. So in case of self-excited, this field winding can be either connected in series with the armature or in parallel with the armature, or it may be a series parallel combination. So based on these construction, they are called as series motor, shunt motor, and compound motor respectively. But in case of separately excited DC motor, that is our experiment, the field winding should be excited by a separate DC source, by a separate source of excitation. Is it clear to everyone? Have you all understood a little bit about DC machine, the working of DC machine?
Yes, ma'am.
Yes, ma'am.
Okay. Now here in this paragraph, many equations are given like VA. This is the armature voltage. This is the expression of torque. This is the expression of speed, omega, right? So there are derivations behind these equations, but this is the fundamental equation. Based on this, you will get this expression of torque and expression of speed, etc. Okay, so following the equation, you will be able to understand that here armature voltage is directly proportional with the speed. Here torque is directly proportional to the armature current. And look at this equation. This is called the EMF equation of the DC motor or DC machine. That is VA is equals to EB plus IARA. Here VA is called the armature voltage, IA armature current, RA is the armature resistance. And what is this EB? EB is called the back EMF, motor back EMF. Okay, now what is the meaning of this back EMF? Like, look at this circuit. This VA is the supply voltage to the motor, right? Once the motor will start rotation after having the current, say I ampere, flowing through the armature winding, what will happen? There will be a voltage developed that is called the terminal voltage across the motor, right? So this terminal voltage will always oppose the cause of production of it, that is the supply voltage VA. Okay, so basically the supply voltage minus the drop IARA is EB, the back EMF. That means VA, the supply voltage is VA here, VA minus IARA is equals to EB. This is the basic fundamental EMF equation of DC machine. Okay. This is the circuit diagram. Theoretical circuit diagram. Here is the supply. 220-volt DC supply voltage. And these two are rheostats, or the variable resistances, or they are also called as potential divider, the voltage divider. This is your DC motor, shunt type. Shunt means here this name shunt implies the constructional design of the machine, right? So basically here field winding is shunted with the armature winding. That's why the name shunt motor. And these two are called brush. This black portion, these two are called brush, right? These brush arrangements are required. I'll explain this part in theoretical class. Okay, why the brushes are required in DC machines. And this is the belt pulley system, which will be acting like a load in this experiment. And look at the figure carefully, you will see that here DC motor is actually coupled with this belt pulley mechanisms, right? So this is called shaft. This is called shaft. So the motor shaft is basically coupled with the belt pulley mechanisms, right? This S1, S2, these are actually the spring balance system. Here, by controlling these two, we will actually apply the load to this motor. And this small r is actually the radius of the pulley. This is the field winding, which is getting excited by a DC source, as you can see. So in the report, you have to draw this circuit, below of which you will draw the apparatus table. I'll provide you the name of the apparatus and their specifications. You will write the name of the device which is under test, that means the DC shunt motor. And in the next table, you will write down the name of the apparatus or instruments, equipments which are required to perform this experiment. Okay. So from this circuit diagram, you will be able to understand what are the instruments you require to perform this experiment. So device under test is the DC shunt motor, and the equipments required is DC supply, ammeter, two ammeters actually. One will measure the field current, right? And this field winding is actually connected with this ammeter via a field external resistance. That means a rheostat is there, by controlling which you'll be able to control the field winding current. And a set of potential dividers, rheostats, are required to be connected with the armature of the DC shunt motor. And armature is connected in series with this ammeter. That means this ammeter will measure the armature current IA, and this ammeter will measure the field current IF. And there is a voltmeter connected across the armature windings, across the DC motor, which will measure the armature voltage VA. Right? And definitely these belt pulley systems are required, which will be acting like a load circuit for this experiment. And a tachometer is required. Tachometer. Tachometer measures the speed. At running condition of the motor, if you place a tachometer along with the center axis of the DC shunt motor, will be able to measure the speed at which the motor is actually running. And this tachometer is digital type tachometer that you will use here in this experiment, and it's a contactless tachometer. That means it is not required to touch the tachometer with the motor shaft. After the apparatus table, you will draw the observation table. This is the observation table. The layout, the format of the observation table is already given to you. So at the top of the observation table, you will write the radius of the belt pulley system, that is small r, which is 75 millimeter, 0.075 meter. It will be required in order to calculate the torque in Newton meter. So here in this experiment, we'll keep the field current constant, will not vary the field current by adjusting the rheostat connected with the field winding. We'll fix the field current at 0.25 ampere. And after that, we'll vary the armature current. That means this column, second column, we'll vary the armature current by varying the load. And load will be given by these two, S1 and S2. Okay. And definitely with the change of the load as well as with the variation of the armature current, the speed will vary because we have seen already the speed is dependent on armature current, right? So speed will be measured by the tachometer, and applied voltage means the voltage across the armature. Definitely when you're varying the armature current, when you're controlling the armature current, you will get armature voltage across the armature terminals A1 and A2, and this will be also kept fixed, right? That means keeping armature voltage, the applied voltage and field current fixed will vary the armature current by varying the load, and in turn the speed will be varied, which will vary the torque, right? So here speed and torque both are varying, and we'll see that speed is indirectly proportional with the torque. So you will calculate the torque with this formula, S1 minus S2 into R into 9.81. And after that, you will plot the graph, speed versus torque graph of DC motor, where speed will belong to x-axis and torque will be in the y-axis. And after the graph, you will write the conclusion. What you have understood from the experiment, from the experimental results, from the graphs, that you will write here under the conclusion section. Okay? Is it clear to everyone?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Now let us see the experimental results. Please wait. Can you see my screen?
Yes, ma'am.
Yes,
Okay.
ma'am.
Okay.
Yes, ma'am.
So this this picture is showing the experimental setup of this experiment number 8 in basic electrical lab, study of the characteristics of a DC shunt motor. Okay, so it's a panel based setup. In the panel, the schematic is given. You can see the schematic of the DC machine. This is the field winding. The coil in series with the rheostat that you have seen in the circuit diagram earlier. So this is the rheostat which is in series with the field winding, that is actually drawn here. And this is the motor A1, A2, these two are armature terminals. These two are armature terminals, right? And these two armature terminals are actually connected with these potential dividers, right? These two are potential dividers. That means these two potential dividers, rheostats. These two rheostats are basically connected with the armature terminals A1 and A2. Okay, this is the meter, the voltmeter, digital type voltmeter, which is used to measure the armature voltage or the applied voltage in the data table. And these two are ammeters, table mounted. They are mounted on the table, so they are called table mounted, tabletop, table mounted analog DC meters. DC meters means definitely moving coil type meter, instruments, meters. Moving coil meters, moving coil ammeters will measure the DC current only. Okay. This is the belt pulley system coupled with the shaft of the DC motor. This is the DC motor actually. So this is S1 in kg and this is S2 in kg, and these two meters, these two dials will be used to measure the value of S1 and S2 in kgs. This is the nameplate of the DC motor, shunt type separately excited DC motor that you will use for today's experiment. It's a 0.5 horsepower direct current motor where AC input voltage can be of maximum 220 volt, right? This is the rating of the field current, 0.25 ampere. These are the rheostats coupled with the armature windings. The rating of each rheostat is 3.3 ampere, 64 ohm. This is the rheostat, the variable resistance connected with the field winding. This is the DC ammeter, will measure the DC ampere, DC current. This is another ammeter. These are the terminals across which the instrument will be connected, the positive terminal, and we have connected with 5 ampere at 5 ampere because the same ammeter can be operated for a 2 ampere range. One is 2.5, another one is 5 ampere. So we have connected this instrument for 5 ampere because maximum 3 or 3.5 ampere current can be measured by using this setup. So we have used 5 ampere current rating. This is the tachometer, the digital type contactless tachometer, which will measure the speed of the machine. And this is the entire setup. And this is the supply mains from Alstom. So these are the instruments, equipments required to perform this experiment. Okay. So at condition, when the power is switched on, what will happen? this handle will be in the upward direction. It means that the circuit is on, the supply is on. This is the tachometer measuring the speed. When you are placing it just near to the motor shaft, it will start measuring the speed at which the motor is running with this LED light that will be automated generated when it is just near to this motor shaft. Okay. These are the apparatus table. You please note down or take the screenshot of this table. DC shunt motor, it's a 0.5 horsepower 220 volt DC, armature current 2.5 ampere, field current 0.25 ampere, and RPM is 1500. Rated speed will be always measured in RPM, revolution per minute. It is 1500. Maker's name is General Engineering and Electrical Works. You please take a screenshot of this table. You need to draw this table in the report. Voltmeter digital type 0 to 750 volt, MECO G, 1 number. Ammeter digital type 0 to 2 ampere, 2 numbers, MECO G. One is MECO G, another one is high tech. Rheostat for field control, wear wound 1200 ohm, 0.6 ampere, 1 number, prompt. Rheostat for armature control 3.3 ampere, 64 ohms, 2 numbers, prompt, and 1 tachometer, digital type. Rating is 0 to 9999 RPM. I think maker's name is Kushum. Maker's name is Kushum. Kusham Meko. Maker's name of this digital tachometer. Have you all noted down the apparatus table? Device under
Yes,
test,
ma'am.
specifications?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. Now look at this spring balance system carefully. The inside diameter will be used here as scale. So the pointer, the scale is indicating the exact zero value. That means 0 kg. When these two pointers are indicating zero value, that means no load is applied here. 0 kg load is there, right? So when no load is applied to this motor, when no load is there, armature voltage is around 178 volt, around 178 volt armature voltage. These two are potential divider used at the armature side. By adjusting these two, you will keep this armature voltage at 178 volt. At this situation, this is the ammeter showing the field current value. It is exactly showing 0.25, ampere. We'll keep the field current at this value because this is the rated field current. Already we have seen it from the nameplate of the DC machine. So we'll keep the field current at 0.25 ampere.
Ma'am, 0.25 or 0.26?
No, it's exactly 0.25. It's not
Hmm.
0.26. Okay, since you are viewing only the the front view, that's why you are getting 0.26, but it is exactly 0.25 if you observe it from the top, because always you need to observe the reading from the instrument by looking from the perpendicular view. Exactly from the top you need to observe. So if you look from the top, you will get it as 0.25 ampere. Okay,
Yes, ma'am.
so it is exactly at 0.25 ampere. And what else? Speed. At this situation, what is the speed? This is the speed. I've got 1496. Rated speed is 1500 RPM. But at this moment, when no load is connected, applied voltage or supplied voltage is just at 178 volt. The rated speed is 1496 RPM. That I have measured by using this digital tachometer during the running condition of this DC shunt motor. Okay. So we'll write this data in the table, in the data table. First voltage is 178. Armature current is
Ma'am, 0.25.
no, 0.25 is the field current. 1496 RPM. Let me check once again the value of armature current. And torque will be calculated by using this formula, S1 minus S2 into R into 9.81 in Newton meter. Armature current, wait. This is the armature current value. This is the ammeter which is measuring the armature current. Okay, we'll use the upper one, upper scale, because we have connected it with the 5 ampere terminal, right? 2 ampere ratings are there, 2.5 and 5. So if you are using 2.5 ampere, you will use the lower scale. But since we are using the 5 ampere current terminal, we'll use the upper scale. So it is
0.3.
what?
0.3.
Ma'am,
Point,
0.28. 0.28.
point, uh, this is 0.2, right? So 0.2, not exactly 0.3,
Ma'am, 0.28.
like that, 0.28 or 0.27, like that. So you please write down it in your data table, what you have observed. I am writing it as 0.28. Okay. So you can measure the torque value. Okay. So this is the ammeter which is measuring the field current. See, it is fixed at 0.25 ampere. And this is the instrument which is measuring the armature current, right? And at this situation, this is the load. See, this is S2, which I have fixed at 0 kg, and I have changed the load, say S1. It is not possible to measure from this picture, but you can see this is the center line, 0 kg, and this is 5. This is 5, right? So 1 kg, 2 kg will see the inner circle, inner scale. So 1, 2, 3, 4, like that. So what is the value? Can you measure it? It is just 1 kg. It is just equal to 1 kg. Okay. So
Yes, ma'am.
when S1 is 1 kg, the left hand side is S1, right hand side is, sorry, we'll consider the left hand side as S2 and right hand side as S1. So S1 is now 1 kg and S2 is 0. And at this situation, what is the speed? This is the value of the speed, 1401. 1401 RPM, right? And the supply voltage will be fixed. Supply voltage will be fixed. Straight. Supply voltage will be fixed at this voltage. Okay. Please note down the armature current. It is equal to 1 ampere. Armature current is 1 ampere. Armature current is 1 ampere. This is 0.5. This is not 0.5. This is 0.8. This is 1.2. And the pointer is indicating 1 ampere. So armature current is 1 ampere when speed is 1401, right?
Yes, ma'am.
1401.
Yes, ma'am.
Yes, ma'am.
This one, 1401 RPM. So this is the second reading. This is the second reading. The supply voltage will be fixed at 178. So this is 1. This will be also fixed. This is 1401. That means after applying of load of 1 kg, the speed is getting reduced by this amount. Find out the difference between these two. And torque will be calculated as you calculate it, it is like 0.73. Next will vary the armature current, 1.2, 1.4, by adjusting the two rheostats connected with the armature. That means when you are giving the load, what happens? This applied voltage, the armature voltage will try to drop down, but it should be kept at a fixed value. That's why we need to control, we need to adjust the rheostats connected with the armature side. 1.6, 1.8. We'll take these 6 readings. Field current will remain same. You will write 0.25 for all the rows, for all the observations. And how will vary the load? We'll keep S2 at 0 kg. for all the readings. Will vary only S1. Like after 1 will take 1.5. After 1.5 it's 1.75. After that it's 2.1. Then it's 2.5. Then it is 2.5. We will calculate the torque in Newton meter using this relationship. The third reading, it is 1.1. So as speed is decreasing in nature, torque is rising. So they are inversely proportional. So if you plot these two parameters in the millimeter graph papers, you will get this type of characteristic curve. Right? Where speed is almost torque is almost speed torque characteristic curve, not torque only. Speed torque characteristic curve is almost constant. It's having a very small slope. It's almost parallel with the x-axis. You should get this type of characteristic curve, but you will draw the curve based on the data you will have from these experimental results. Okay, next you see the next reading, that is 1.5. See, this is 1, this is 2, so it's just in between 1 and 2, so it's 1.5. At this situation the speed is 1387. The speed is, please note down the speed, at 1.5 kg it's 1387. Applied voltage is fixed at 178. And what is the armature current? What is the armature current? It is in between 1.2 and 1.6.
1.4.
1.4, right. It is kept at 1.4 by adjusting the rheostats only. So what is the speed? 1387 or 88.
Yes, ma'am.
187. Okay. Next, again we'll vary the load. Now it is 1.75. So at this situation, the speed is 1360. 1360. Speed is 1360. Okay. And armature current is 1.4. Now again, when armature current is 1.6, this is the situation, this is the load. It is at 2.1 kg. It is not possible to measure it directly from the screen, but it is at 2.1. And this is the value of the speed, 1345. 1345 RPM. When the load is, when S1 is 2.1 kg and armature current is 1.6. 1345 RPM. And last is when armature current 1.8. This one. This is 1.6, this is 2. So this is 1.8. So when armature current is 1.8 amps, this is the case. Load is 2.5. Load is 2.5. This pointer is indicating just in between 2 and 3. So it's 2.5. And this is the value of speed, 1329. 1329. 1329. Okay. So it
Yes,
is
ma'am.
1329 Before that, 1, 3, 4, 5. Before that, 1, 3,
60.
6, 0, and before that, 1, 4, or 1,
1387.
1387.
1387. Correct. You calculate this torque. Calculate the torque, and then try to draw the speed torque characteristic curve in plain paper. You will be able to understand that what is the actual shape of the characteristic curve. What is the value of torque for the third reading? Not third, fourth one.
1.2.
1.2. For second last, what is the value?
1.5.
1.5. For the last reading,
1.8.
1.8. So you can see that here in this motor, the torque is directly proportional to the armature current. As the armature current is increasing, the torque is also increasing in nature. So this is a characteristic of shunt motor. Shunt motor. Let me draw the basic block diagram of a shunt motor. This is the connection diagram of a shunt motor. So this is the DC supply which is connected across the armature. This is actually your motor. And this is armature resistance, RA. Armature resistance in series with the motor armature terminals. So this branch is representing the armature of the motor actually. So IA is the armature current flowing through the armature resistance. And what is the total current? Total supplied current, total DC current, that is IL. So this IL is actually equal to sum of IA plus I field, right? Because these two branches are parallel in nature. Your shunt field winding, this is actually your field winding. Your shunt field winding is just in parallel with the armature terminals because it's a shunt motor, right? And since both the windings, both armature windings and field windings are excited from the common DC voltage source, this type of separately excited motors are exactly similar to that of DC shunt motors, right? Because as per the definition of separately excited DC motor, the field winding must be excited by a separate DC source, right? But if the DC field winding, if the field winding of the separately excited DC motor gets the DC input voltage from the same source which is connected with the armature winding also, The same separately excited motor will be called as DC shunt motor. So basically there is no difference between DC shunt motor and separately excited DC motor. Okay, that's why the speed torque characteristic curve is same for both the motors, for both types of motors, right? Where line current is exactly equal to the sum of two currents, armature current and the field current, and torque is just proportional to the armature current. And what is speed? What is the relationship of speed in RPM? It is equals to, it is proportional to EB by phi. Phi is the flux. And what is EB? The back EMF, which is equals to V minus IA RA. Right? That means speed is also proportional to the back EMF because the flux is constant. This flux is constant. Why this flux is constant? Because this flux will be coming from the field current. We have kept field current constant at 0.25 ampere. Once the field winding is excited from a DC circuit, then only a flux will be created. Right, which is kept constant at 0.25 ampere. So your speed is exactly proportional to the back EMF, or it is exactly proportional to V minus IA RA. Okay. Do you have any questions, any queries from the experiment?
No.
No, ma'am.
Then we have to draw circuit diagram.
No, ma'am.
Yes, you have to draw circuit diagram. This circuit diagram. You will draw this circuit diagram, which is given in the classroom. And here you will draw the speed torque characteristic curve. Torque will be in the y-axis and speed will be in the x-axis. Speed in RPM, capital N is the speed in RPM. Speed will be in the x-axis, right? So from 1300 to 1500, we will vary the speed. So when it is 1329, just at this position, torque is say 1.8. After that, it is decaying. As the speed is increasing, the torque is decaying like that. So it's having a drooping characteristic. So it is at a very low slope, right? So it is almost in parallel with x-axis because your speed is, your torque is just proportional to the armature current.
Ma'am, at 1496 torque will become 0.
At
1496. When the speed is 1496, torque will become 0.
what you will do, you will not take this observation while you are plotting the graph. You will not take this reading set. Why? Because this is the situation when no load is connected. We'll draw this speed torque characteristic curve only at loaded condition. We'll not consider this no load situation in the graph. If you consider this, you will get this type of graph. Because no load characteristic curve is something different from the loaded characteristic curve. So we'll take only these readings while we are drawing the graph. Okay? I forgot to mention that. You will not take this one while we are drawing the graph. Okay, if you do not have any questions, Neetudi, are you there? You can take the attendance now. Yes,
Yes,
please
okay.
take the attendance. Please take the attendance.
Okay. Respond on your attendance. Roll number 1. 1 Tejas Advik.
And Neetudi, one more thing, please mark those students who are absent for the last 2 or 3 consecutive classes.
Okay.
Mark them if they are absent consecutively for 2 or 3 classes, 2 to 3 classes. And I hope all of you have submitted all the pending laboratory reports.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, very good. So those who haven't submitted after the internal examination, that means by this weekend, try to submit all the pending reports. Okay, Mitudi, please carry on.
Yes. Marmik Agrawal, roll number 2.
Present, ma'am.
3.
Present, ma'am.
Ma'am,
Four.
roll 1.
Roll number 3 is Farhan Ahmed.
Ma'am,
Present.
you skipped roll 1.
Roll 1 Tejas Advik.
Yes, ma'am.
Okay. 4.
Present, ma'am.
5.
Present, ma'am.
6.
Present, ma'am.
7. 7 Shubhranil Banerjee. Absent. 8.
Present, ma'am.
9. Roll number 9 Shoham Basu. Absent. 10
Present, ma'am.
Pushpendu Bera. Present.
Yes, ma'am. Present.
11.
Present, ma'am.
12 Sattam Bhattacharya. Absent. 13 Abhirup Bishwas. Absent. 14
Present, ma'am.
15
Present, ma'am.
16
Yes, ma'am.
17
Yes, ma'am.
18
Present, please, ma'am.
19
Present, ma'am.
20
Present, ma'am.
21 Anushrita De. Absent. 22
Present, ma'am.
23
Yes, ma'am.
24
Present, ma'am.
25
Present, ma'am.
26
Present, ma'am.
27
Present, ma'am.
28
Present, ma'am.
29
Yes, ma'am.
30
Present, ma'am.
31
Yes, ma'am.
32
Present, ma'am.
33
Present, ma'am.
34
Present, ma'am.
35
Yes, ma'am.
36
Present, ma'am.
37
Present, ma'am.
38
Present, ma'am.
39 Shagnik Mukherjee. Absent. 40
Present, ma'am.
41
Present, ma'am.
42
Present, ma'am.
43
Present, ma'am.
44
Present, ma'am.
45
Present, ma'am.
46 47
Present, ma'am.
48
Present, ma'am.
48 Kirti Sharaf. Present. 49
Present, ma'am.
50
Yes, ma'am.
51
Present, ma'am.
52
Present, ma'am.
53
Present, ma'am.
54
Present, ma'am.
5.
Present, ma'am.
Completed.
Okay. And one more thing, students, please note that from the data table, from the observation table, if you draw the speed versus armature current graph, speed versus armature current graph, speed in the y-axis and armature current in the in the x-axis, what you will get? You will also get a straight line type characteristic curve, right? Slightly decaying in nature, but the graph will be almost in parallel with the x-axis, right? Because if you see the data table, you will see that your armature current, as armature current is rising, the speed is decaying, right? So if you draw the speed versus armature current characteristic curve, you will also see a drooping characteristics, but the curve is just in parallel with the x-axis. So it means that your motor, your separately excited motor, which is just like a DC shunt motor, because if you see the circuit diagram, you will see here only one DC source is used to excite both the windings, both armature and the field windings. Though in case of separately excited motor, field winding needs to be separately excited, but here we have used same common DC source voltage, right? So that's why this separately excited motor is just like a DC shunt motor, which is having almost a constant speed characteristic curve in variation with the armature current. If you plot speed versus armature current, you will get this type of
Ma'am, armature current is in x-axis.
in x-axis, right, and speed in y-axis, right?
Ma'am, then two graphs.
No, you don't need to draw the second graph. You will draw only the first one, this one, speed torque character. I'm saying that
Okay, ma'am.
if you draw it in your notebook, you will see the speed will be constant throughout the operation as your current is varying, armature current is varying. It means that this type of drives, this type of DC machines give constant speed characteristic curve. So these machines are mostly suitable for the applications where constant speed is required. In different type of applications, in many applications like in milling machines, in fans, in conveyors, in lathe machines, constant speed motors are required, right? So
Yes, ma'am.
in these applications, these motors, these type of separately excited DC motor, shunt type DC motors are widely used. Okay, once you are doing experimental machine, you must know that where you should apply the motors, the machines, why you are learning, why you are studying the characteristic
Yes, ma'am.
in the machine. That's why I'm telling. Okay. So if you do not have any questions, any queries, students will stop here. Thank you, everyone.
Thank you, ma'am.
Thank you,
Thank you,
ma'am.
ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you,
Thank you,
everyone.
ma'am.
Thank you, ma'am.
And Oishi, are you there?
Yes, ma'am.
Oishi,
Yes.
I have seen your message. You have sent a message, right?
Yes, ma'am.
A numerical problem. Okay, I'll solve the problem and after that I will send the screenshot to you.
Okay, ma'am. Thank you, ma'am.
Where you have sent the post in the common group?
In the common group.
Okay, okay. Give
Okay,
me
ma'am.
some time. I'll solve it. Then I'll provide you the solution. Okay.
Thank you, ma'am.
Okay.